Hello, my name is Joy Osborne. I'll be presenting using alternative gases for VOC analysis. Today I'll be discussing the basics of using different carrier gases, the initial setup with hydrogen as your carrier gas, and then setting up nitrogen as your purge gas, and comparing the purge gases helium versus nitrogen, and then comparing using different carrier gases for VOC analysis. Just to start it off, I wanted to go over a little bit about helium and why we're doing this. Helium is used for many purposes besides VOC analysis. The problem with helium is that it's difficult to find and store, and this is because it is a byproduct of natural gas drilling, so there's only a limited resource of it. Because of this, the prices have increased and shortages have been reported for helium. So demand for alternative gas analysis has increased. Unfortunately, the choice carrier gas is helium, but hydrogen does provide the best separation and the fastest analysis time. As you can see from the Van Deemster plot, you're probably wondering why we chose hydrogen over nitrogen. And this is due to the fact that hydrogen has 4 times faster analysis time. The optimal linear velocity is 40 centimeters per second. So this allows us to be good for a variety of retention times, just like in an 8260 list. Nitrogen has a steeper Van Deemster curve and narrow velocity range. So as the pressure increases, you lose phase efficiency, resulting in poor separation. The advantages of hydrogen, like we talked about, is the cost, because it can be derived from tanks and generators. The tanks are usually a little cheaper than helium tanks, and the fact that you can get it from water makes it a lot more cost efficient. The generators usually can pay for themselves within 1 to 2 years, but can last 5 to 7 years. And because it comes from water, it's a renewable resource. And also, like I said from the Van Deemster plot, it has a faster runtime. The disadvantages of hydrogen. Unfortunately, hydrogen, since it hasn't been used as much as helium, there isn't as many established methods for it. It is also a flammable gas, so safety has to be a concern for you. It is not as sensitive as helium. There's about a 40% loss of sensitivity, so it's not as good for trace analysis. It's also a reactive gas, unlike helium. And because of that, you'll see later on there's some problems with tuning and other things. And since you need a larger volume of hydrogen on your column, you're going to need more vacuum. So when you're initially setting up with hydrogen, this can take some time and it can be a little bit difficult. So we do want to stress that to you. You may need some new hardware changes, but each GC manufacturer has different stipulations for that. So you may want to check with your GC manufacturer on what needs to be changed. We also recommend that you use new stainless steel tubing and new filters. And this is because hydrogen is a reactive gas, so if there's any residual impurities from using helium in your gas line, it will have the ability to react with them and kind of clean out the system. And also a turbo pump is needed. Like I said earlier, since you're using more volume of it, you're going to need a stronger pump. So a turbo pump is definitely recommended. You also need to consider your column, what kind of GC column you're using. You definitely want to use an inert column. Like I said, it's reactive, and a narrow bore column. All the typical GC columns you would use for VOC analysis are fine, your 624, your VMS, etc. And then again, safety. You definitely want to leak check and make sure you check with the GC manufacturer that it is explosion proof just in case something does happen or has a hydrogen sensor built in. And this is something we observed while setting up with hydrogen. There's definitely a settling in time is what we like to call it. So from when you're switching from helium to hydrogen, it may take some time for it to kind of settle in, and your background to go down. It could take even a few days. After that, you may need to even clean that source since it has that scrubbing reactive quality to it. Anything in those lines or on your column or anything like that would hit your trap or hit your detector rather. So you may need to clean your source. And tuning was also a little more difficult with hydrogen. Again, because it's reactive, you have more problems with some of your ions. We observed with our BFB tuning, which is required for 8260 and 524, the 96 to 95 ion ratio is the hardest to achieve. Factors that we have found that helped us pass BFB tuning was lowering the column flow, using a higher amount of methanol, and using a higher level standard. And this is because you're using more BFB, so there's less hydrogen in your background when you're tuning. This may need to be investigated further for US EPA use. And again, just to go over the methodology, just so you know that 8260 doesn't have a defined carrier or purge gas. So you probably can use nitrogen as a purge gas and hydrogen as a carrier gas, but please consult your auditor. Unfortunately, 524.2 and 524.3 do have a defined carrier and a purge gas, which is helium, so you definitely want to consult your auditor for that one. So first we're going to talk about the easy part, which is switching the purge gas to nitrogen after you have your carrier gas switched to helium. It's extremely easy to do with the atomics, and actually our software will leak check it and calculate the flow rate differences for you. And we found that there was no significant changes to our purge and trap methods that you would use for any of the VOC methods. Here's an image of our atomics. It is a purge and trap auto sampler. It has an 80 sample carousel. It's used for soil analysis, water analysis, or it can do methanol extraction. And like I was talking about earlier, it's very easy to switch to the purge gas with atomics. And actually, you can do that in the software. You just go to Tools, Configurations, you click the Options tab, and then you click Nitrogen, and it will calculate the difference between flow and pressure for you. And this is due to the fact that we have a patented electronic mass flow controller in our systems, and that is pictured on the right. And after you get it hooked up to nitrogen, your atomics, you're going to want to leak check it. Also very easy to do with our software. All you have to do is hit leak check. It will pressurize the system to 25 psi. We'll seal the system, and then it will wait to see if there's a loss of 1 psi over a minute. If there is, it will fail. As you can see in here that it passed. And here's where the atomic leak checks. It actually leak checks the whole soil and liquid sample pathway for you. If you were to fail, it will go into subsystem A, B, and C, and then from there you can narrow down where your leak is coming from. All right, for this first study, we compared the purge gas only, so we haven't even switched the carrier gas yet. And again, we did this on soil and water side, and we compared the percent RSDs, the minimum detection levels, and the response factors from switching just the purge gas. Here are the atomics parameters we used to evaluate this. Everything that's in yellow is turned off. As you can see, it's very typical VOC type parameters that you would use on the atomics. You have 11-minute purge time, 40-minute purge flow. Here's it on the soil side. The things I wanted to point out is it is a little bit different on the soil time. We do recommend that you heat the sample. Here we heated the sample to 40 degrees C. And then to increase the dry purge time, on the water side it was half a minute, and on the soil side we increased it to 1 minute dry purge time. Here are the GC mass spec parameters we use for this study. Again, very typical parameters. We use a VRX column, 80:1 split ratio, really nothing out of the ordinary. Here's a total ion chromatogram of a 50 ppb water standard. Blue is purged with helium, red is purged with nitrogen. As you can see, there is really not much difference when you purge with either gas. Here's the same thing on the soil side. Again, you can't really see much difference between helium and nitrogen purge. And here are the overall results we got from this study. There's a little bit of statistical variation, but we didn't see anything out of the ordinary. That's an advantage using helium or nitrogen as your purge gas. All right, and here's the next study we did, which we, swapped out the carrier gas to hydrogen and swapped out the purge gas to nitrogen. We evaluated methods 8260, 524.2, 524.3, and we used the atomics in conjunction with two commercially available GC mass spec systems, and I'll discuss the results with you. Here are the GC mass spec parameters we used for this study. For system 1, we used a 60:1 split ratio. We used a VMS column. We used the same GC method for 8260 as for 524.3. On the other system, the second GC system, we used a slightly different method. The only difference we used was with 8260, we used an 80:1 split ratio, and for 524.2, we used a 150:1 split ratio. And this is just due to the fact that for 524.2, we used a 25 ml sample volume. And here are the atomics conditions we use for US EPA 8260. Again, very typical conditions, nothing really out of the ordinary. Purge time 11 minutes, purge flow 40 mils a minute, dictated by US EPA 8260. And here are the atomics conditions we use for 524. 524.2 is on the left, and 524.3 is on the right. I did want to again point out to you the slight difference between point 2 and point 3. For point 2, we used a 25 ml sample volume, and for point 3, we used a 5 ml sample volume. And also, point 3 is a little more flexible about how the purge time and purge flow. So we could get a faster analysis time. We did reduce the purge time down to 8 minutes, but we also increased the purge flow to 55 mils per minute, so you get about the same amount of purge volume. Here's a total ion chromatogram of a 10 ppb 8260 standard. And I just wanted to point out that we used the same exact GC parameters for this, but as you can see, hydrogen gave you a little bit faster run time. And again, these parameters have not been optimized for how fast hydrogen can run. Here's another example with a 50 ppb 8260 standard. As you can see, hydrogen again has a faster elution time, and it has not been optimized to see how fast actually hydrogen can run. Just to go over a US EPA 8260, it's used to analyze volatile organic compounds in waters and soils and sludge-type matrices. It uses a Purge and trap autosampler with a GC mass spec. It requires a BFB tune every 12 hours, and it requires the use of internal and surrogate standards. To be able to pass the requirements for 8260, 90% of your compounds have to have an RSD of less than 20% or an R-squared value of above 0.99. And then I'll also discuss with you the results we got from minimum detection limits. Again, I just wanted to go over the BFB tune, and that was a little more difficult using hydrogen. As you can see on the top, it's failing. Our 96 to 95 ratio is a little high. So it did take us a little more time to get that to pass. On the bottom, you can see it passing, but that was with a calibration standard. And like I discussed earlier, it does seem to help use more methanol or a higher level standard to get that to pass. Again, with 8260, it requires internal and circuit standards. With atomics, we have 3 standard vessels that are able to spike each sampler standard with a 1, 2, 5, 10, or 20 microliter standard. And it uses the same technology as an inkjet printer, so it's very accurate. Right, and just to go over the 8260 calibration results, most of all the compounds on 8260 had less than a 20% relative standard deviation. Both systems that we ran it on showed bromomethane had to be linear regressed, but it still was above 0.99. On one system, naphthalene, ethyl methacrylate, amyl acetate, hexachlorobutadiene, and naphthalene had to be linear regressed. Even with that said, more than 90% of the compounds were less than 20% RSD, which meets the 8260 requirements. You can also check out our application note for more details. Here are results from 8260, or minimum detection limit results. We ran a 1 ppb standard and 7 replicates, and we found that all passed except for tert-butyl alcohol. In order for it to pass, it had to be less than 1, and this is because tert-butyl alcohol has a poor purge efficiency. And then we also compared our relative response factors, which they talk about in 8260. As you can see, there is a slightly lower relative response factor using hydrogen, and that's due to the loss of sensitivity you get from using hydrogen. All right, so just to go over US EPA 524.3 again, it measures the volatile organic compounds in drinking water. You have to have a BFB tune at the initial demonstration of capabilities, but for 0.2, it has to be done every 12 hours like with 8260. It also uses internal and circuit standards. For this method, all the regression values of the calibration curve must be greater than 0.995. And it also requires a precision and accuracy study. And for 524.3, it also states that the samples must be held at 10 degrees C while you're running them. Fortunately, with atomics, it comes with an optional chiller tray that can actually hold your samples at 4 degrees C, so it's required for 524. And here's an example of a BFB tune from 524. We were able to get the pass. And here are the results we got from 524.2. We ran a 0.5 ppb to a 50 ppb standard and a 9-point calibration curve. From that, we calculated the percent RSD. As you can see, everything is less than 20% or has a linear regression value of above 0.995. And here are the calibration results for 524.3. Again, we ran a 9-point calibration curve from 0.5 ppb to 50 ppb. As you can see, all the compounds had a greater R-square value than 0.995. And here is an extracted ion chromatograph on the top using hydrogen. And I just wanted to show that you still get really good separation using hydrogen as your carrier gas. And here's the precision and accuracy study that we did for 524.3. We did a midpoint calibration, which was a 10 ppb standard, run in 8 replicates. For this, you had to get between 7 and 13 ppb average concentration to get that plus or minus 30% average percent difference. As you can see, all the compounds passed this precision and accuracy study. So in conclusion, it may take some time to initially set up and tune with hydrogen, but we were able to meet the criteria for 80, 260, and 524. There may need to be more consideration from the U.S. EPA for BFB tuning to make this more readily available to use hydrogen. And unfortunately, 524 is still written that helium has to be the carrier in purge gas, so you definitely want to consult your auditor. In the future, since hydrogen has a much faster runtime, we're going to look into running to see exactly how fast we can run those VOCs using hydrogen. And we think we can do it, much faster than we have been for these examples. So stay tuned for that. Does anybody have any questions?